Section 7.3, graphical solutions of linear programming problems with two variables. Okay, we have one vocab word this section, and it is a bounded set. A bounded set is a feasible region. It's the shaded area of your graph if it has a boundary on all of its sides. If it doesn't have a boundary on one of its sides, then it is said to be unbounded. So if we had axes here and our region was this, that is bounded. It has a function or an inequality trapping each of the sides. Otherwise, it is unbounded, and that means it goes off toward an infinity or negative infinity in at least one direction. So, steps for solving linear programming problems. Now we're actually going to solve the entire problem. Most of these steps you've already done. So, step 1, graph the feasible set for the problem. That means that you're going to graph your linear inequalities, you're going to shade, and you're going to figure out where they overlap. Part 2, determine the corner points of the feasible set. If you have put one point directly on top of another point, then you can take the coordinates directly from your graph paper. If not, you're going to have to use substitution, elimination, or matrices to solve for x and y for the corner points. And then step 3, evaluate the objective function at each corner point. So you're going to take each of your corner points and you're going to plug them into your objective function. If the set is bounded, the maximum and minimum will occur at a corner point. That's perhaps the most important part of today's lesson. If it is bounded, your maximum and minimum will be a corner point. You just have to determine which corner point it is. If it is unbounded, then you need to test additional points on the edge of the feasible set to determine if the max or min even exists. So if your bounded region, let's say it looks like this, unbounded region looks like this. It has 3 corner points. You will plug in and test all 3 corner points. If this one, let's say we're looking for our minimum. If this number right here is the smallest number and it is trapped between 2 bigger values in the objective function, then you have in fact found the minimum. But if the minimum is one of the corners, then that gives the opportunity that as you travel along this edge, the number actually even gets smaller. So if you're looking for minimum and the minimum occurs at one of the outer corner points, then you need to go test one more point further out to verify that this one was actually the minimum. If this point further out is smaller, then it just means it has no minimum. And that's probably the hardest part of this section, is what to do when it's unbounded, and we'll practice that. So let's look at example 1. What point in the feasible region maximizes p for the objective function p equals x plus 3y? Well, first thing we got to do is we got to graph these all. So let's start here with x plus 2y equals 5. Well, using the intercepts, x equals 5. So put a point at 5. Y, 2y equals 5. So y equals 5/2, which is 2.5. Now understand that's a decimal, but here let's think about the slope. We go down 2.5 over 5. 2.5 over 5 is 1/2. So knowing that the slope is negative 1/2, we can now get more points along our graph. And we want to go as far in each direction as we can, with the hope that we double a dot, that we put 2 points on the same graph, or on the same point. These are all solid lines, so I'm ready to connect. Let's test 0, 0. Test a point not on the line. So I'm going to test 0, 0. 0 plus 2 times 0 is less than or equal to 5. 0 is less than or equal to 5. That is true. So we're shading below the pink. All right, next one, let's try green. X minus y is less than or equal to 2. Using the cover-up method, let's make this equal. Using the cover-up method, x equals 2, and negative y equals 2, which means y equals negative 2. Y crosses at negative 2, x crosses at positive 2. We go up 2 over 2, so the slope is 1. And good news, I don't know for sure if we'll need that corner point, but I did just put a green dot on top of a pink dot. All right, let's see here. Let's test 0, 0. 0 minus 0 is less than or equal to 2. 0 is less than or equal to 2. That is true. So we're shading above the green. All right, x is greater than or equal to 0. The line x equals 0 is a vertical line. That is the y-axis. So if x is greater than or equal to 0, a lot of times when it comes to the vertical and horizontal lines, I just think of which side of this line has x is bigger than 0. It is the right side. We can test 0, 0, or we can test a point, maybe 1, 1. 1 is greater than or equal to 0 is true. But most of the time, because it is just a vertical line, we're kind of good to just shade to the right side. Here, y equals 0, that's a horizontal line. And we want y to be greater than or equal to 0. So again, we could test the point 1, 1. That's true. We're shading above. So which part of the graph is pink and green and purple and blue? Is this part right here? We color that part in extra, extra, extra dark. That is our feasible set. Okay, we need the corner points, and there are 4 of them. What we're going to do is we're going to make a T-chart with our corner points and our objective function. So I'm going to put it right here. This is going to be the corner, and this is going to be x plus 3y. That is what we're trying to maximize for our objective function. And good news about these corner points, I think these are all nice, pretty points for us. So the first one is 0, 0. We did not double dot because we used the x and the y axes as our blue and purple, but where do the x and y axes cross? 0, 0. The next corner point is right here. That is the point 2, 0. I put a point on the green graph where it crosses the x-axis. That is the line y equals 0. That's a graph. That's a point. Then the point 3, 1. I double dotted that one. That was a point for the pink and a point for the green. And the last one is not technically a double dot exactly, but it's an intercept. And because we use the intercept method, we know that is the point 0, comma 2.5. We put that point on the graph as an intercept. Now we take these and we plug them into our objective function. So 0 plus 3 times 0 is 0. 2 plus 3 times 0 is 2. 3 plus 3 times 1, 3 plus 3, 6. 0 plus 3 times 2.5, 7.5. So the question of which one maximizes the objective function, and we look at the question carefully. It says what point maximizes. So this is the maximum, but it occurs at 0, comma 2.5. And since it says what point, we want our answer to be the point, not the value. All right, example 2. Find the largest value of x plus y for x and y satisfying the constraints. So I'm going to skip the trivial constraints for the moment, and I'm going to focus on the other 3 slightly more complicated ones. So the first one is x plus 2y equals 6. Using the cover-up method, we get an x-intercept of 6, a y-intercept 2y equals 6, so y equals 3. X is 6, y is 3. The slope here is down 3 over 6, so that's negative 1/2. And you saw in the last example where we very quickly were able to get all 4 corner points without using any other methods other than looking at the graph. So although it is a gamble, you might not need all those points. You might, and it might be helpful to you. Let's test 0, 0. 0 plus 2 times 0 is greater than or equal to 6. 0 is greater than or equal to 6. That is false. So we are above the pink line. All right, next one. Y minus 4 equals negative 4. I'm sorry, x, wow, that wasn't even remotely what it says. X minus y equals negative 4. So x equals negative 4 as one intercept. Negative y equals negative 4 for the other. So that means y equals 4. So the y-intercept is 4. The x-intercept is negative 4. Up 4 over 4 means a slope of 1. Oh, we didn't double dot there. But, okay, it might be okay. We'll just see. Let's test 0, 0. 0 minus 0 is greater than or equal to negative 4. 0 is greater than or equal to negative 4. That is true. So we're on the side with 0, 0, which is below the green line. So far we're looking at this area here where they're overlapping. Let's go again. 2x plus y equals 8. So using the cover-up method, 2x equals 8. So x equals 4. And y equals 8. So x-intercept of 4, y-intercept of 8. The slope here is down 8 over 4, so that's negative 2. And we get our line. I think this blue graph will determine whether we are bounded or unbounded. So let's test 0, 0. 2 times 0 plus 0 is less than or equal to 8. 0 is less than or equal to 8. That is true. So we're on the left side of the blue. Now, where the blue, pink, and green overlap, we've got this triangle going on here. The last two constraints to worry about. X is greater than or equal to 0, and y is greater than or equal to 0. Well, if x and y are both greater than or equal to 0, that means we're talking about quadrant 1. Right? This top right part of the graph, it's not a coincidence that the other quadrants aren't as large or visible. Not a coincidence. You're only really using quadrant 1 because x and y both have to be positive. So we're talking quadrant 1 as our final area that we're shading. So goes down the left, down the axis on the left, the pink, up the blue, and then down the green. I'm double checking because the reason I'm double checking this is that x being greater than or equal to 0 was helpful to us. Y being greater than or equal to 0 is actually not affecting this region, right? We never go below y equals 0. Although we have 5 inequalities, we only end up with a quadrilateral with 4 sides. So we're only using 4 of them. So I just want to double check that we're getting the right things here. X is 4, y is 8. Yeah, I think we're good. We end up with a quadrilateral. So now we need our corners and our objective function, x plus y. Now, it didn't call it an objective function. It also didn't say maximize, but it said largest value of x plus y. So that's how we know that that is our objective function. Are any of the corners easy to identify? Well, this corner right here was actually a point on our graph. Because we use the intercept method, that is the point 0, 3. And right above it, again, using the intercept method, we got 0, 4 as a corner point. The other two, this point right here, is not double dotted. Darn, that means we got to proceed. That is the green with the blue. That is x minus y equals -4 with 2x plus y equals 8. Okay, this isn't too bad. This is set up very nicely for the elimination method. We get 3x, the y's will cancel, equals 4. So x equals 4/3. And then let's see here, I would want to plug it in probably to the green one. 4/3 minus y equals negative. I'm going to go ahead and change that to negative 12/3. I know I'm going to need common denominators here, so might as well go ahead and change -4 to negative 12/3. That means, oh, I'm out of space here, negative y equals negative 16/3. So y equals 16/3. So our x is 4/3, the y is 16/3, and then I just want to double check. 4/3 is like 1.3 approximately. Yeah. X value is just a smidge bigger than 1. 16/3, it's like 5 and a little bit. And if you look at the height, we are just above 5. So it's about in the area that we solved it to be in, which is a good sign. One more corner point. Pink and blue. Blue was 2x plus y equals 8. Pink, x plus 2y equals 6. All right, we got to get some opposite coefficients here. I'm going to go ahead and just change the pink. I'm going to multiply it all by -2. So -2x minus 4y equals -12. -2, -4, -12. And then I can add down. The x's cancel. We get -3y equals -4. Y equals 4/3. All right, when I go to plug it back in, I'm going to plug it into the original pink one. I think that sounds good to me. X plus 2 times 4/3. Could put a little divider there. Help your teacher out. Equals 6. X plus 8/3 equals 18/3. X equals 10/3. Now, I was squeezed for room here. You are always welcome to ask for more paper if it's like a test or a quiz, or use plenty of paper if you're doing homework. But I did fit it in, and what I'm doing when I get to the end is, because I know it is squeezed in here, and the less work I show, the more likely I am to make a mistake. So I'm going to check 10/3 is like 3 and a little bit. Is the x value 1, 2, 3 just to the right of 3? And the y value is just over 1, which is 4/3. Looks good to me. Let's go plug our corner points in. X plus y. So 0 plus 3 is 3. X plus y. 0 plus 4 is 4. X plus y. 4/3 plus 16/3 is 20/3. X plus y. 10/3 plus 4/3, 14/3. Now, are we trying to maximize or minimize? Largest. 20/3, that's what, 6.6 repeating. That looks to be the largest value. 20/3. Now, what we're asked for in the end does very specifically depend on the question. So here it says find the largest value of x plus y. So this question specifically is asking for the largest of these numbers, of the x plus y numbers. Oftentimes it says find the point that makes the value the largest, in which case your answer would be your corner points, not your objective function values. Now, just want to remind you, there are a lot of opportunities here to make a mistake, to plot the wrong point, to say, I mean, you heard me say this one, I wrote one thing and said another thing completely. Lots of opportunities, even if you know what you're doing, to make a mistake. So be sure to show your work. Example 3. You run the Coca-Cola bottling plant. You profit $20 per case of regular Coke and $25 per case of vanilla Coke. The table below shows the number of machine hours and man hours needed to produce one case of each type of Coke. It also shows the maximum number of hours available. Find the number of each type of Coke that can be produced in order to maximize profit. Then determine the maximum profit. Okay, example 3, this is kind of the big deal. This is, they don't give you anything here. They're not giving you inequalities. They're not giving you a picture. We got to do it all. So let's define variables first. Find the number of each type of Coke. So I'm going to write it up here. let x equal and y equal number of cases of regular and number of cases of vanilla. Okay, our objective function, I'm going to put that one up here too. I just have a feeling here space might be limited down here, so I'm trying to put some of it up here, the ones that are kind of not needed for the moment. The objective function, find the number of each type of Coke that can be produced to maximize profit. So max profit. So we need a profit equation where $20 per case of regular and $25 for vanilla. So 20x plus 25y. All right, now we need some constraints. What prevents us from being able to make 1 million of each? See if I can zoom out a little bit. Well, we have a maximum hours. So we have maximum hours of machine and maximum hours of man time. So the machine is 54 hours. So that means we're going to have less than or equal to 54 hours for the machine, which is 3 for regular and 2 for vanilla. So 3x plus 2y. Then for the man hours, we have 75 man hours. So we can't go over 75. It's 4 for regular, 3 for vanilla, 4x plus 3y. Although the chart might be a little confusing at the beginning, you got to figure out what it's telling you. I do actually like it better than having it in the words. Makes it easier for me to find the numbers I need. We have the trivial also. You can't have negative cases of Coke, which means these two right here that we're only in quadrant 1. These quadrant 1. So if you look at the graph paper, it is already in quadrant 1. We're good to go. But we got to get these graphed. So let's start with the pink. 3x plus 2y equals 54. So 3x equals 54. 54 divided by 3. Let's see here. 3 goes into 30 10 times. The difference from 30 to 54 is 24. 3 goes into 24 8 times. So that means x equals 18, 10 plus 8. 2 goes into 54. 2 goes into 50 25 times. It goes into 4 2 times. 25 plus 2 is 27. Ooh, do we have enough to count up to 27? Let me see here. Let me put some marks as we count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to double check that. 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Ooh, it goes up to 30. Okay, we might be good to count by ones. That would be convenient, kind of. 3, 4, 5, 6, 7, 8, 9, 10. Let's double check on the x-axis. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. According to the machine hours, we are good to count by ones. Let's check out the man hours and make sure we're good there also. 4x plus 3y equals 75. Let's do y first. 75 divided by 3. Y is 25. We're still good. 75 divided by 4. Okay, 80 divided by 4 is 20, which means 76 divided by 4 is 19. So this is 18.75. Now I'm multiplying in my head real quick. 4 times 18, that's 40 plus 32, that's 72. And then 3 more to get to 75. 3 out of 4 is 0.75. Okay, well, this will fit. It'll fit. That's the first thing I want to be optimistic about here. Okay, let's graph them. X is 18 for the pink. Since I marked every 10 when I counted, I can just go to 20 and go back 2. Please don't count up to 18 if you have them marked. Y is 27, so here's 30, 29, 28, 27. For this one, I am just going to grab a ruler and connect them, or a straight edge as it may be, because I don't really want to count that many points out. Could it work? It could work, but is it worth the time? I mean, maybe it is, and maybe I'm going to regret this, but I'm just going to connect those. That's a lot of points to put on the paper, and not necessarily a slope that's quick to access. Let's test a point. Should have left room. Test 0, 0. 3 times 0 plus 2 times 0 is less than or equal to 54. 0 is less than or equal to 54. I'm going to put a check mark there. That is true. So we're below the pink graph. And oftentimes, the fact that we have maximum constraints that we can't produce or use over this machine hours and man hours probably means we are bounded, that we can't produce a million cases of Coke, that there will be a limit to what we can do. That usually implies bounded. Let's test the green, or get the green graph. Y is 25, 10, 20, 1, 2, 3, 4, 5. And X is 18.75, which is just to the right of the pink, right there. And using our straight line, straight edge, yeah, approximately like that. So the green and the pink do cross. Actually, it looks like maybe they cross right there. But without having double dotted, I don't know. And furthermore, the slope of the green line, it went down 25 and over 18.75. This is not going to be a pretty slope. And the amount of time that it's going to take me to deal with that, I would probably rather just calculate that slope or calculate that point. Let's make sure that we're shading below. Test 0, 0. 4 times 0 plus 3 times 0, less than or equal to 75. That is true. So we're shading below the green also. We're also in quadrant 1 because of our trivial constraints. So our region, I wonder if I can grab a thicker marker here for coloring, goes down the left side, across the right, goes up the pink, and then switches to the green. This region right here. Okay, so we need our corner points. And our objective function, 20x plus 25y. Okay, let's start with the easiest. 0, 0 is a corner. We actually have 3 easily accessible points because we went over to the pink point right here, which was the x-intercept for pink. That was 18. So that is the point 18, comma 0. We also have the top, which was the green graph y-intercept, and that was y equals 25. So that's 0, comma 25. And then the last one, we do have to figure out where the green and the pink crossed. So let's see here, I'll see if I can put that down here. 3x plus 2y equals 54. Put a little line here to separate this step. There we go. Oops, I forgot this part. Oops. Okay. And our green, 4x plus 3y equals 75. Well, that is unfortunate. Nothing's going to immediately cancel. So we need to get common coefficients or opposite coefficients ideally. I think getting rid of the y will have smaller numbers that we're multiplying by. So I'm going to multiply the entire top equation by 3 and the bottom equation by -2. So you get 9x plus 6y equals 150 plus 12, 162. And then for the green, you get -8x minus 6y equals -150. When we add those down, the y's cancel. The x's, conveniently 9 and -8, we just get x equals 12. And then I'm going to do a quick check. There's 10, 11, 12. 12 is right about in here. And it's not actually where they cross exactly, but it's close, maybe. I was expecting it would cross more like at 10, but it's close. It's in the general vicinity. If I got 20 or something like that, I would be concerned. But it's pretty close. I did use, a piece of cardboard to draw my lines. So I'm going to accept that answer. But we do still need to find the y value. I'm going to plug it into the pink. 3 times 12 plus 2y equals 54. That's 36 plus 2y equals 54. 54 minus 36 is 18. Divide by 2, y equals 9. Let's check. Could that be about right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's actually that point right there. And on my graph, I can very distinctly see a pink and a green next to each other. But it's pretty close. So the last point was 12, 9. Now, all of these points need to go into your objective function. So 20 times 0 plus 25 times 0, 0. This one, 20 times 18 plus 25 times 0. 20 times 18, that's 2 times 18, which is 36. So we get 360. I wish I would have scooted it over just a little bit. Actually, I might just start to the left of the line here. 20 times 0 plus 25 times 25. 25 times 25 is 625. I know that because 5 times 5 is 25, times 5, most people know. So 5 cubed is 125. This is 5 times 5 times 5 times 5. 5 squared times 5 squared. So it's 125 times 5. The last one I may have to do a little bit more work on. 20 times 19 plus 9 times 25. 20 times 19. 2 times 19 is 38. So this is 380. Yeah, it makes sense. I'm double checking. 20 times 18, I got 360. 20 times, oh, why did I put 19? 20 times 12. There we go. 2 times 12 is 24, so this is 240. 9 times 25. 4 25s make 100, so 8 make 200. So this is 225 for a total of 665. Okay, what are we trying to do here? We are trying to find the max profit. Find the number of each type of Coke that can be produced in order to maximize profit. We want the max profit. That looks to be 665. And we want to know how many of each type of drink need produced. So that's 12 regular, 9 vanilla, 4 665 profit as our final answer. This particular question wanted all 3 things. These questions, they're a lot. None of this, again, is anything, maybe you didn't do the objective function before in school, but the majority of this you have seen before in previous math classes. Okay, let's try example 4. Minimize the function 3x plus 5y with the feasible set defined by quadrant 1, x is greater than or equal to 0, y is greater than or equal to 0. This is quadrant 1, which is why the picture is the way it is. Otherwise, we have some decimals. That's fun. So let's get these graphed. First thing to graph. At least this one doesn't have a story problem, which is nice. It gives us our inequalities, which is nice. Okay, let's see here. 0.8x plus 0.2y equals 90. So cover up. 0.8x equals 90. 0.8x equals 90. And 0.2y equals 90. Now, I'm writing this one down because this one is something that is, a little outside of my comfort zone for solving in my head. 0.2y, that's 1/5. Y equals 90. When I write it as 1/5, that is more comfortable to me. Multiply both sides by 5. 90 times 5 is 450. This one here, 0.8 is 4/5 x equals 90. Multiply by 5, divide by 4. So we're multiplying by the reciprocal here. And x equals 450 divided by 4, which is 112.5. All right, well, I'm thinking our graph paper probably doesn't go up to 450 or 112.5, but we will come back to that in a minute. Let's get our other one graphed. I'm going to leave a little bit of space to come back and test a point. Normally, I would just do it line by line, equation by equation, or inequality by inequality. But because we don't have numbers on our graph paper, and we're clearly not going to be able to count by ones, I kind of want to know what our scope is before I determine what I want to count by. So this one looks better. 3x equals 600, so x equals 200. 6y equals 600, so y equals 100. So it looks like our x needs to go up to 200, and our y needs to go up to 450. Let's see here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. This one has 23 marks. So I could count by tens this way. All right, let's see about going up this way. I'm going to mark them this time when I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one goes up to 30. If I count by tens here, that's 300. That's not going to be enough. So maybe count by 20s this way. So when I go by 10, 20, 40, 60, 80, 100. So this is 100. This would be 200. 1, 2, 3, 4, 5. This is 300, 400, and 500. Whew. And then this one here, I can count by tens. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that'd be 100, and this is 200. The units on each axis don't matter as long as you are consistent along each axis. So the pink crosses at 112.5, so I'm going to say that looks to be right about there. And it crosses at 450, which looks to be right about there. I'm going to use the cardboard straight edge again to get a graph. And we're going to test 0, 0. So testing 0, 0, 0.8 times 0 plus 0.2 times 0 is greater than or equal to 90. Test 0, 0. Forgot to write that down. We get 0 is greater than or equal to 90, which is false. So we are shading away from 0, 0. The right side. Okay, now the green. Let's test 0, 0. 3 times 0 plus 6 times 0 is greater than or equal to 600. 0 is greater than or equal to 600. That is false. Also, I didn't graph the green line yet. Let's graph that real quick. X crosses at 200. Y crosses at 100. Okay, it's not very steep, but it's there. Y is at 100. X is at 200. I guess the scale I use helps it not appear to be very steep, but we are shading away from 0, 0 there. Now, knowing that we are in quadrant 1, we have a region that overlaps that goes down here to the pink, goes along the pink, along the green, and then along the x-axis. And we're looking at this region here as our final answer. Okay. Let's see. I got to color it in a little bit better than that as my final answer. Okay. This region is an unbounded region. So let's get some corner points and test them and see what happens. So corner, 3x plus 5y. Okay, so our corner points, some of them are a little, well, what do we have so far? We have 1 here, 2, and 3. This corner point is from the pink graph, and it is the y-intercept of the pink graph, which we have over here is 450. So that's 0, 450. This corner on the bottom right is the green graph x-intercept, which we have as right over here, 200. So that is the point 200, 0. Now we still do need to figure out where the pink and the green graph intersect, where they cross. So let's see here. I'm going to separate this part, and I'll put it here. 3x plus 6y equals 600. That's the green. And the pink is 0.8x plus 0.2y equals 90. Let's see here. What can I make the 0.8 and the 2? So I'm going to just first multiply the bottom equation by 10. 8x plus 2y equals 900. That feels a little bit better to me. Now we have a 3 and an 8, or a 6 and a 2. So I'm going to multiply the bottom equation by negative 3. That'll give us negative 24x minus 6y equals negative 2700. And the green graph, 3x plus 6y equals 600. When we add those together, we get negative 21x equals negative 2100. Divide both sides by negative 21, x equals 100. And I take a quick look here. Does it look like they could cross at 100? That looks like a good x value. So now I got to go back and plug it in. 3 times 100 plus 6y equals 600. So 6y equals 300, y equals 50. Does it look like the height could be 50? Yeah. So 100, 50. We got to plug both of these, or all three of these, into the objective function. So 3 times 0 plus 5 times 450. 5 times 400 is 2,000. 5 times 50 is 250. So 2,250. Yep, okay, so 3 times 200 plus 0 times 5, 600. And 3 times 100 plus 5 times 50. That is 300 plus 250. So that's 550. What are we trying to do here? We're trying to minimize. So the smallest number here, this was 600, this was 550, is this point 100, 50, 300 for 550 right here, 600, I'm just double checking. So minimize the function. So the min is 550 at 100, 50 is our answer. Now, this feasible set is unbounded, but look at where the minimum is. It occurs at this corner point right here, which means as we go here, the number gets bigger. As we go here, the number gets bigger. Since it gets bigger in both directions, we are okay to only test those points. Example 5, it's good news because we are still using the same functions, the same inequalities to get our same feasible set with the same corners. So we can just go ahead and jump to the corner part. The corners were 0, 450, 200, 0, and 100, 50. And we're trying to minimize 5x minus 3y. So all we did here was we changed our objective function. So 5 times 0 minus 3 times 450. 3 times 400 is 1200 plus 150, so that's negative 1350. 5 times 200 minus 3 times 0. 5 times 200 is positive 1000, so definitely not the minimum. 5 times 100 minus 3 times 50. This is 500 minus 150, so 350. We're trying to minimize, so this here appears to be our minimum. But what it means is look where 0, 450 is located. In the graph, 0, 450 is up here. This point has a very special situation going on. It is right here, the edge before our feasible set goes off to infinity. So because it's the point closest to going to infinity, which would be here, it would also be down here at 200, 0. But because it's on the border of going to infinity, there might be a better point out here where the answer gets even smaller. So we need to pick a point further out on this boundary, further up the edge of our region. You can pick any point you want, but I would recommend a point with some easy numbers. So I see this is 0, 450. I'm thinking 0, 500 is further. So let's go back to our chart and plug in 0, 500 and see what happens. I'm going to label this min, question mark. 5 times 0 minus 3 times 500 is negative 1,500. Our min got smaller, right? We thought the min was negative 1,350, but as we went toward infinity along the boundary, our number actually got smaller. If we were to go even further, and this isn't needed, but if we were to go further, 5 times 0 minus 3 times 600, negative 1,800. It gets even more negative. It gets even smaller. So what this means is that there's no min. As we went along the border, the number got smaller and then smaller again, which means the further we go out, the smaller it'll get. There's no minimum here. If we had plugged this number in and it had gotten bigger, then that does mean that negative 1,350 is the minimum. But because it got even smaller, this one has no minimum.